from our formula when we were talking about the mean, we know that the mean of our event is going to be each event times the probability. So we have 0 times its probability, 0.061, plus 1 goal times its probability, 0.154, plus 2 times its probability, 0.228. These are all coming out of the table. Plus 3 times 0.229, plus 4 times 0.173, plus 5 times 0.094, plus 6 times 0.041, plus 7 times 0.015, plus 8 times 0.004, plus 9 times 0.001. When we total this all up, our mean is going to be equal to 2.851. What this is saying to us then is, on average, a randomly selected team would score 2.851 goals in a game if this process was repeated many times. Because remember, this probability is talking about taking large samples. So experimental probability is one thing, but when you want to talk about what's happening as a general rule, you want to say that this has happened numerous times. So in this computing of the standard deviation, we calculate the variance. Remember that the variance we use as sigma squared. And so we're going to take the value minus the mean. So we just calculated the mean. It was 2.851. We're going to take each event. So the events are the goals scored. So that was 0 through 9, right? 0 through 9 goals. And we're going to subtract off the mean and then multiply by each of those individual probabilities. So I have, in the first event, 0 goals scored minus 2.851. I square that, and I multiply it by its individual probability, which was 0.061. And I keep going for all of these different events. So plus 1 minus 2.851 squared times its probability, which was 0.154, plus... Nope. 2 minus 2.851 times its probability of 0.228. So variance and standard deviation, as you can see, is kind of cumbersome. Plus 3 minus 2.851 squared.
Is there a way to do this on the calculator?
I'm sure if you want to type some things, then you can for sure do that. Times 0.229. But remember, when you're doing this for the AP exam, the reader needs to know what you're doing. Plus 4 minus 2.851 squared times its probability, which is 0.173, plus 5 minus 2.851 squared times its probability, yikes, 0.094, plus 6 minus the mean, 2.851 squared times its probability. Is that 0.041? Thank you. Plus 7 minus 2.851 squared times its probability, 0.015, plus 8 minus 2.851 squared times its probability, which was 0.004, plus 9 minus 2.851 times its probability, which was 0.001, for a grand total of 2.6648. Now this is the variance. And if you want the standard deviation, of course, you have to take the square root of that. So the standard deviation is equal to the square root of the variance. So this is the square root of 2.6648, or in other words, my standard deviation is 1.632. So really this is saying, on average, a random team from a random game will have its number of goals scored differ 1.632 from the mean number of goals scored. Amazingly enough. So in this slide, we're going to be talking about something called a continuous random variable. And in the beginning of the lesson, I mentioned that the thing that's different about a continuous random variable is that the probability of any individual event is 0. So as you look at this, really what they're talking about is area under the curve, or we also call it probability, likelihood, percentages, that kind of thing. And so a continuous random variable takes on all the values in some interval, and that's kind of the big idea. There's an interval. Here in this picture that we see below, they have a rectangle, but we're going to be working with the normal distribution for the most part. And when you talk about a density curve, it doesn't have to be a curve. So for example, this picture, they could call a density curve on your test. They use the word curve liberally. And the probability of any event under that density curve and above make up that event. So here we see a shaded area, and that area is 0.4. That means the probability of that event occurring is 0.4, or there's a 40% chance that that would occur. All continuous probabilities give 0 to the likelihood of one individual outcome. That's different than the discrete situation. So the probability of one thing happening out of 7 billion is nothing, because there's no area under the curve. In order to have area under the curve, you need 2 x values. That's why the probability is 0. You probably should star that. This is only to do with a continuous random variable. So how does this work? Down below here, you'll see that they talk about the likelihood, or the probability that your event is going to occur between 0.3 and 0.7. So the likelihood that that's going to happen is 0.4 in this case. And so that's what they're talking about right here. So the most common density curves is the normal curve. For example, the weights of 3-year-olds closely follows a normal distribution with a mean of 30.7 and a standard deviation of 3.6. So these are kind of important things that when you see that, mean 30.7, standard deviation 3.6. And randomly choose one 3-year-old female, call her weight X. Let's find the probability that this randomly selected female weighs at least 30 pounds. So as you write this thing, this at least part, you would say, what is the probability that the event, which we're calling X, is to be greater than or equal to 30? Now, in order to do this, you have to have a z-score. So we're going to find the z-score. Oh yeah, they never go away the rest of the time you're in this class. So the z-score is the event that you're talking about, which was 30, minus the mean, which was 30.7, divided by the standard deviation of 3.6. When you find this value, hopefully it is negative 0.19. Which means that this thing that I'm talking about here, the probability of x being greater than or equal to 30, is really the probability that your z-score is greater than or equal to negative 0.19. Because remember, in statistics, we're always trying to normalize data. We really can't do a good job of describing what's happening unless we can fit some kind of standardization to that score, whether it be weights, heights, IQs, whatever. So when you do this, you can actually type this thing into your calculator. So we know that this would be the same thing in our calculator as normal CDF. And you could go from a z-score of negative 0.19 to 99. That's talking about how many standard deviations you are away. And when you get done, you find out that that value I have from my sources, 0.5753. So check that out. If you're looking at a picture of this thing, what this is saying is if I look at that normalized curve, and I look at my z-score of negative 0.19, I'm talking about all of the shaded area here. That's what I'm talking about on my normal distribution. So in this last part, I'm finding the probability that my randomly selected person
Oh, the mean is 30.7
and 29. And of course, that means that you have to find the z-scores for each of these. So the z-score for 27 will be 27 minus 30.7 all over 3.6. What z-score do we get for this one? Okay, negative 1.028. And then if I look at the other z-score, my other z-score would be 29 minus 30.6 all over 3.6, or sorry, 30.7, pardon me, over 3.6 for a grand total of? Negative 4.472?
Yeah.
472. So really my probability that I'm talking about is saying this. What is the probability that my z-score is falling between negative 1.028 and negative 0.472? And if I want to, I can type that into my calculator as a normal CDF, and I just type in the z's, because when you're normalized, you just type in the z-scores. So negative 1.028, comma, negative 0.472. And when I get done, I should get an answer of 0.1677.
Yeah.
And if I were to look at a picture of this, which I don't have here, but if I were to look at a picture, my picture would look something like this. Can you guys please be quiet? Thank you. Here are my two scores. Negative 1.028 and negative 0.472. And I'm talking about the shading in here. What's the likelihood that that's going to occur? And that's the 0.1677.